All right, so this week we're going to take a look at something a little different. Okay, we're going to look at graphing. So we're going to kind of get away from like solving equations and using a lot of algebra. This week's going to be a lot more visual. So what we'll do is for homework, everything this week will be a worksheet. Okay? We give you just a few problems with a grid already on the worksheet, and that'll be it. Okay, it's just gonna be graphing. So if you are going to be absent any day and you need a worksheet, I do have the 3 worksheets we're going to do this week already printed. Okay, just let me know. So the 2 graphs that we're going to focus on drawing are the graphs of sine and cosine. Okay, we've studied other trig functions besides just sine and cosine. Mason, can you tell me one of the trig functions we've studied besides sine and cosine?
Tangent.
Yeah, we studied tangent. We're not going to look at the graph of tangent. Anybody else name another one we've studied? Besides sine, cosine, tangent? Yep. Yep, we did secant, we did cosecant, we did cotangent. Okay, we're only going to focus on sine and cosine. So what I'm going to kind of do today is give you general background information about sine and cosine. And then specifically, we're going to get into a different transformation each day. Okay? So what we might do, I think today what we're going to do is we're going to shift the graph left and right. Okay? So we'll look at how do you do that? Okay? Where do you have to add a number into the equation to shift left and right? Tomorrow we'll take a look at shifting up and down and also stretching. So if that's your original, that would be considered a vertical stretch because you made it taller, or you could compress it. Okay, so we'll look at that one. And then we'll also look at compressing and stretching left and right. So a lot of these I can kind of show you with this program. So if you look at the wave, shifting left and right, it looks something like that. Okay? It's moving left and right. And that would have an effect on the sound. So we'll kind of talk about what these things would sound like as well. This is an example of compressing. Okay, they go like this, horizontally, and then stretching it back out. And then the last one I kind of showed you, compressing or stretching vertically. Okay, the only one I can't really show you or demonstrate with sound is shifting up and down. There's really no direct connection to sound for that one. Okay, that's kind of what we'll look at that as we go through the week. All right, so first thing, these kind of functions are called periodic. Okay, they're a lot different than the kind of functions you probably went over like in Algebra 1, like drawing a parabola or a line, okay, things like that. What periodic means is it means things repeat. Okay? So what happens is when you draw these functions, you're going to get a bunch of different y values. It's going to go through a range of y values, and I'll show you that in a second. And then after a certain amount of time, it's just going to repeat those same values again. So basically what we keep seeing is the same y values repeated in this graph over and over. We're not going to use, nor do you really need a graphing calculator for this week. But to quickly show you a sketch of something, it kind of helps for me to use it. All right, so let's take a look at this. Okay, this is the graph of sine. Okay, it's a connected function, meaning if you were to draw it, you never have to lift your pencil to draw it. You can just start at one point, and it's like a wave. Take that. And what I want you to focus on is this section that I'm tracing in red. Okay, if you notice, it starts at 0. It goes up to its highest value at 1. Then it starts going back down to 0, keeps going down to -1, and then it comes back up to 0. After that section I just described and that I just drew in red, that same section is going to repeat again right there. And then it's going to repeat again right there. And it also repeats in the other direction. It's the exact same y values repeated over and over. How long before it repeats? Well, I put this right here. This particular graph, and the way I drew it, from here to there. That's the amount of x values it has to go through before it's going to repeat itself. And that width, that line from here to here, has a name. Okay, and we'll talk about that in a second. Questions on that idea of why it's periodic? That the idea that it keeps repeating itself. Okay. So the length of that interval, okay, that I drew right here in black, the amount of time that it takes before it's going to repeat, that's called the period of the function. Okay, and we can, when we draw our function, we can mess around with the period. Okay, we can make it a really long period. Okay, so that's a wave that's been really stretched out, and now it has to go a lot further before it starts repeating. Or I can take that, excuse me, and I can compress it, maybe. Like that. So now it's compressed, and now the period is a lot shorter. So the amount of time it takes to go through all the different values is much shorter. So that is called the period. Now, the normal period, if you don't do anything to the graph, you just graph the basic sine or the basic cosine function, the period is 2 pi. And does anybody remember what 2 pi is in degrees? Yep.
360.
360. So this graph has to go through 360 degrees before it repeats itself. And in fact, if on my calculator I'm in radians, but if I start at 0 and I end at 2 pi, if I just draw you a picture from 0 to 2 pi, you will see exactly 1 period of the function. Okay, what I'm showing you on the screen right there, that's considered 1 period. And when I have you guys sketch it, that's how I'll have you do it. Okay, on paper, not with a calculator. But you're only going to have to sketch 1 section of it. Okay? We know that it goes on forever in each direction, so we got to just limit how much we're actually going to sketch. Okay. Any question on the idea of what the length of the period is if you don't mess around with it, if you don't do anything to it? Okay, it's always 2 pi. We're not going to change that until Thursday. Every problem we do until Thursday will always have a period of 2 pi. Okay, this idea I kind of already mentioned to you when I described periodic, but if you were to graph it beyond what you're seeing in that window, you're just going to see this again. It's just going to repeat. So let's say I wanted to go all the way to 4 pi. So now instead of stopping at 2 pi, I'm going to look at twice as far. Well, now you're going to see 2 periods. There's the first one, stopping at 2 pi. And there's the second one, stopping at 4 pi. Okay, so the graph just repeats. That's all. And another name you might see for a period is a cycle. Okay, 1 cycle of the graph. We generally call it the period, but there are some different fields or disciplines that use the word cycle. Is anybody in electrical? In electrical? So when we talk about electricity, there's a couple of things you can talk about. You talk about voltage. That's not really what we're getting at. So the voltage in these outlets is 120 volts. But it also operates at a certain amount of cycles per second. Anybody know what that is? Yeah?
60.
Exactly. 60. And in electricity, they usually don't call it cycles per second, but it has a name abbreviated with that. But does anybody know what that stands for? Yeah?
Hertz.
Hertz. 60 hertz. That's 60 cycles every second. So in the US, that's what electricity operates on. It cycles 60 times per second, assuming you're dealing with alternating current, okay, the kind of current in your house, not the kind of current in your car. That's direct current. So I'm just showing you, you might see that word used in other disciplines, but we don't generally use it as much. But the idea of hertz, we do use that. Okay, that's something you might have seen if you looked at the program I had. Okay, when you talk about a sound frequency, it's measured in hertz. Okay, that's the pitch of the sound, how low pitch or high pitch of a sound you have. Okay, and we have a range of different pitches we can hear. And we'll look at that too later in the week. We'll see what you can hear. Also, if you think about like cell phones or especially like landline phones, when you press a button, you hear a sound. Well, that sound is a frequency. It's a certain frequency. So you can kind of trick a phone into thinking you're pressing buttons when you're not, if you generate the right frequencies. Okay, you can kind of manipulate a phone. So if we have some time, I might show you some stuff with that too. All right, so when you want to graph, let's say you're graphing a line. Okay, in Algebra 1, very simple to graph a line as long as you have 2 points, okay, because lines they're straight. Well, trig functions are curved. Okay, so in order to get a real good idea of what it's going to look like, we like to get 5 points. Okay, and I refer to these as like the 5 critical points or the 5 important points to making a sketch. So what I like to do is find where it starts, where it stops, the highest point, the lowest point, and what's right in the middle. If you can find those 5 points, that's going to give you a pretty good sketch. Other thing to keep in mind is these sketches don't have any sharp turns to them. Okay? Everything you sketch with trig functions should be nice and smooth. Okay? Nothing goes like that. Okay? So when you sketch any trig function, just try to sketch it as smooth as you can. All right, so in order to graph either sine or cosine, you have to know where it starts before you do something to it. Okay, so if I say to you, for example, I want you to shift the graph of sine up 1. Well, it's very easy to shift it up 1 as long as you know where it would be to begin with. So that's what we're going to look at. I'm going to give you 2 basic tables, one for sine, one for cosine. These 2 tables are going to be the starting points. Anytime you want to do any transformation, you're going to go back to these 2 tables. Okay, so let's start with sine. And I showed you the x values that I picked. Now, these x values, they're not just random numbers. They're nicely spaced numbers. Peter just told us That's 360. 0 radians is the same as 0 degrees. Pi over 2, that's 90. 180. And 3 pi over 2 is 270. For this week, you got to get used to working in radians. Okay, I put the degrees up there just to show you that these are nicely spaced, every 90 degrees apart. Okay, so what we can do is we can use our calculator and figure out what the y values would be. If you plug in 0 for x in the sine function, let's see what we get for y. Okay, and remember, I have to do it in radians because my calculator is in radians. Okay, so for the sine of 0, I just typed it in. You got 0. Let's try sine pi divided by 2. You get 1. Okay. Don't worry about cosine yet. We'll come back to that one. So just to show you where these first 2 points are, that's 0, 0. This is pi over 2. And it's up at 1. And does it look like the graph goes any higher than the number 1? What do you think, Bob? No, it never goes higher than 1. So that might give you a hint at how low it's going to go in a second. Okay, the next one is pi. Okay. Pi is right there. What do you think would be the y value if I plugged in pi? Page? Yeah, I would get 0. Very good. 3 pi over 2. Okay, I'm going to scroll back up. 3 pi over 2 would be right here. Now, we didn't do that one, but based on symmetry, what do you think 3 pi over 2 is going to be? Yeah, Alex?
-1.
Yeah, it's going to be -1. So 3 pi over 2 is -1. And then 2 pi, you're back where you started. That's the end of the period, and now it's going to repeat. So my y value right there is 0. So anytime you want to do a problem involving sine, think of this as your starting point. Start with those values, and then if you want to shift everything up, down, left, or right, you modify those values accordingly. If you're going to shift things up and down, it's going to affect your y values. If you're going to shift things left and right, those are your x values. Okay. Any questions on that original table? Okay, let's look at cosine. Okay, so I've got a graph of sine. I'm going to graph cosine at the same time. I want to see if you can tell me what's the difference between sine and cosine. Anything, Peter?
They're offset from each other like 90 degrees-ish.
Yeah, that's exactly right. They are phase shifts of each other, which is what we're going to study today, of 90 degrees. That's what they are. So you could either say, well, if you shift the blue one left 90 degrees, or shift the red one right 90 degrees. Either way. But other than that, sine and cosine are exactly the same type of look. Any other trig function doesn't look like that. Okay. Tangent looks totally different. Secant, cosecant, cotangent. So we don't study those in intro to trig. We don't really have enough time to spend. We'd have to spend probably a week and a half or 2 weeks if we were going to do all the trig functions. Okay. So let me get rid of sine so it looks less confusing. Let's just look at cosine. And what I can also do is let's make it so we don't see 2 sections of it. Let's just look at 1 section. And what's the name of it? It's not really a section. What do we call it? It's 1 period or 1 cycle. exactly. So let's set it up for 1 period. Okay. And we've got the same x values. Let's see if we can figure out our y values. So there's 1 point, that one, and that one. Okay, so Connor, could you tell me what my y value is at the first point?
It'll be 1.
Yep, it'll be 1. Irene, how about the y value at my second point?
0.
Yep, we're down at 0. Emily, the y value at my third point?
-1.
Yep, -1. So now we've hit the low value. Connor, my next y value? 0. And my last y value, Ryan?
Back at 1.
Back at 1. Those y values are just going to keep repeating. 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0, 1. They just keep repeating. Okay, so anytime you want to do a problem involving cosine, you're going to start with the table on the right. Okay, one mistake sometimes I see is I ask a problem about, say, sine, and they start with the wrong table. So make sure if it's a sine problem, you use the right table, use the correct table. If it's a cosine problem, use the cosine table. All right, so after you have your original table, okay, you know where the graph is starting, then you have to determine where it's moving to. Again, in this class, we don't really have enough time to get into really complicated transformations. So we only do one transformation at a time. What that means, if we shift the graph up, that's all we're going to do. We're just going to shift it up. We're not going to shift it up and shift it left at the same time. That'd be two things at the same time. Okay, we only do one transformation at a time. So, because we're only doing one transformation at a time, only one column is going to change in that table. Either you're going to do something that affects the x values, or you're going to do something that affects the y values, but not both. Okay, it's going to be one or the other. Okay, so for every transformation we do, the values in one column will stay the same. The values in the other column will change. Now, it doesn't have to be like that. You can do problems where you say shift the graph up, you shift it left, and then you stretch it. Do all three things at the same time. And in pre-cal, I get into that because we spend 2 weeks on it. In this class, we only spend 1 week because it's a half year. Okay, so for every transformation we do, one column stays the same, one column changes. If you were going to shift something up and down, what values would that affect? Does shifting up and down affect x values or y values? Y values, yep. So if I gave you a shift up and down, you don't have to worry about doing anything to the x's. All you're going to do is copy them down from the tables I just gave you. All right, so that's kind of the general background information about sine and cosine. Now, specifically, I'm going to focus on one transformation, which is called a phase shift. So a phase shift, easiest way to probably explain is show it to you first, and then we'll write it out. But a phase shift is when you just drag the graph basically left or right. You're not you're not stretching it, you're not compressing it. All you're doing is taking what's there and sliding it to the left or to the right. Another name for that you might see in geometry, that's called a translation. You just translate left or right. Okay, so now we hopefully have an idea of, when I say phase shift, what that means to do. But for each transformation, you have to know how the equation is modified. Like, if I wanted to do a phase shift of 90 degrees to that cosine function, well, where do I put the 90? I gotta throw 90 in there somewhere. Do I add it? Do I multiply it? What would I do? And for a phase shift, depending on which way you want to shift, left or right, you either add or subtract it inside the parentheses. Okay, so if you want to shift a graph left or right, you either add or subtract inside the parentheses. Okay, so here's an example of a phase shift. That's a phase shift by pi over 2 radians. Or you could say it's a phase shift by 90 degrees. But now the question is going to be, which way is plus going to shift it, left or right, and then which way is minus going to shift it? Does anyone have a guess which way plus is going to shift it? Which way? Yeah.
Right.
All right. You might think, like, if you have a number line, positive is right. What's the other option? Ashton? Left? Well, one of those two. Let's take a look at it. Let me take sine of x, and then let me take sine of x plus pi over 2. And let's see what it looks like. There's the original. There's the shift in red. Which way did the blue graph move? It moved left. Okay. The blue graph was moved to the left when I added. So it's not what you would always expect. So if the graph is going to move left when I add, it's going to move right when I subtract. Okay, there's 4 transformations we're going to study. 2 of them do exactly what you would expect. Kind of common sense. 2 of them do the opposite of what you would expect. This is one of the transformations where common sense doesn't work. Okay? It's the opposite of what you would expect. Okay, so you can put that on a reference sheet, use it on the test, but somehow you got to remember that. Okay, so if you have x minus a value, your graph is going to shift right by the value, okay, whatever you type in. If you have x plus a value, your graph is going to shift left by the value. Now, technically, you can shift by whatever you want. You could shift by 12 degrees, 14.7 degrees, but there's common shifts that we usually do. The common ones are 45, 90, and 180. They're not the only ones, but they're just the ones that we do most often. And in radians, that would be shifting by pi over 2 for 90, pi for 180, or pi over 4. That would be for 45. All right, so we'll look at, eventually we're going to do a shift with pi over 2. We'll do a shift with pi, and then we'll do a shift with pi over 4. So we'll try each of the common ones. I'm not going to do each one left and right. Okay, I'll just pick one or the other. So, how do we figure out, last steps, how do we figure out where those 5 points in the table are going to move to, okay, to make our new sketch? So what I'm thinking of is how do we figure out how to modify these tables? Well, first thing is the y's stay the same. If you're going to shift something left or right, it doesn't affect the y's. That's up and down. So the first step, depending on whether you're doing a sine problem or a cosine problem, is to go back to one of the two tables I just showed you and copy down the y values into your new table. You don't have to do anything to them. Just copy them down. What they were before is what they're going to be now. But if the y's are going to stay the same, what's going to change? The x's. Okay, the x's are going to change. So you're going to take all the original x's and you're going to do something to them. Okay, you're going to change them. How do we change them? First thing, let me show you in an actual problem. Actually, I won't do that. Okay, the first thing is determine what has been added or subtracted. So I'm going to just go to the next problem and show you that, and then I'll come right back to this. Determine what has been added or subtracted. That's what you've subtracted. You've subtracted pi over 2 in the next problem. And now, once you know what you've added or subtracted, remember phase shift does the opposite of what you would think. So we subtracted pi over 2 in the next problem. I am going to add pi over 2 to all the x's in the original table. Okay, so look at your problem, look what's been added or subtracted, and do the opposite of that to all the original x's. And that's the only transformation we're going to do today. And I don't want you to think that every transformation we do all week is always going to be the opposite. It doesn't work that way. For phase shift, it is. For some of the other ones, it's not the opposite. So you just have to remember this one is the opposite. Okay, everybody have the steps? All right. Okay, so let's make a graph of x minus pi over 2. Okay, the first step, even though you don't have to do it today, is to recognize what kind of transformation is that. Are we shifting left and right? Are we shifting up and down? Are we stretching the graph? What are we doing? Well, I've only taught you one transformation, so it's the one I've taught you. On the test, they'll all be mixed together. Okay, all the types of problems we learn all week. Okay, but that one is shifting left and right. Eric, what's the name of that when you shift the graph left or right? What do we call it?
Phase shift.
Exactly. It's a phase shift. Okay, so what I've done is I copied down the original table. That was a couple slides back. So we didn't have to keep flipping that. So there's my original. Now I'm going to set up my new table. When we do a phase shift, what values are not affected at all? What values do we leave alone? Just copy them from the original table. Yeah, the y's. Okay. So what I'm going to do, because the y values are not going to be affected by a phase shift, is copy them down from the original table. 0, 1, 0, -1, 0. And for each value you get right in the table, that's how I grade it. So this table is worth 10 points. 5 x values, 5 y values. For every value you get right, you get 1 point. So if all you could do was write down that the y values didn't change, you'd get half the credit for the table, just filling in those 5 values. Okay, now you're going to figure out the x values. How about Victoria? What did I add or subtract to x in this case?
Pi over 2.
And did I add it or subtract it? I subtracted it. Okay, in the original problem, it's been subtracted. So what am I going to do to all the original x's? Let's go back, just double check. So step 2, figure out what's been added or subtracted and do the opposite. So what would you do? What's the opposite of subtract pi over 2? We're going to add it. You're going to take every x value in this table and add pi over 2. So off to the side, I'm going to put the calculation. What I would actually be grading is inside that box. So 0 plus pi over 2. Pi over 2 plus pi over 2. Pi plus pi over 2. 3 pi over 2 plus pi over 2. And 2 pi plus pi over 2. You are adding pi over 2 to everything. Okay, so the first one is pretty straightforward. 0 plus pi over 2 is just pi over 2. Mason, what's pi over 2 plus another pi over 2? So we already have a common denominator, right? So that's good. We don't have to find a common denominator. So we can just add them directly. 2 pi over 2. Okay? So we get 2 pi over 2, which is just pi. Okay, now the next one. Ileana, do we have a common denominator between pi and pi over 2? No. What's the denominator on pi, even though it's not there right now? We can always make it a 1. So what would be the common denominator between 1 and 2? 2. So we are going to double the bottom, double the top. So now I have 2 pi over 2 plus 1 pi over 2. That's 3 pi over 2. Okay, the next one, Connor, do I already have a common denominator?
Yeah.
Yep, common denominator is already there. So what's 3 pi over 2 plus 1 pi over 2?
4 pi over 2.
Perfect, 4 pi over 2. And can you tell me what that would reduce to?
Just 2 pi.
Just 2 pi. And the last one, same one I just asked Ileana about, we don't have a common denominator. So Emily, what would I have to multiply top and bottom by? 2. So that gives me 4 pi over 2 plus 1 pi over 2, which is?
I was just asking.
Yeah.
Sorry, I wasn't saying what.
What do you get when you add that?
3 pi over 2?
So we got 4 pi over 2
Oh, that's 4, 5 pi over 2.
plus 1 pi over 2 is 5 pi over 2. Okay. And there's your table. So 1 point for each x, 1 point for each y. Now if you look at the x's, there's a pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. What do you think the next one would be? 6 pi over 2, and then 7 pi over 2, 8 pi over 2, 9 pi over 2, we could keep going. So what I do a lot of times is, once I do the first 2 or 3, I find the pattern, and I use that to figure out the rest. That's how I do it. Once you reduce it, you don't see the pattern. Okay, we don't leave it as 2 pi over 2. We don't leave it as 4 pi over 2. That's a good way to see the pattern, but you always want to reduce it as much as you can. Okay? Okay, so any question on those values? Bless you. Okay, so those are your table, and now the last step is to put those tables on your graph. Peter, what's the highest and lowest that our graph goes?
1 and -1.
1 and -1. Now, you can label your x-axis however you want, but whenever you label something on a graph, what do you have to make sure of when you put your labels? You have to make sure that all the labels are equally spaced. So you could go 2, 4, 6, 8, 10, 5, 10, 15, 20, however you want to equally space it. Well, we're going to equally space it using those values. They were all equally spaced. Does anybody remember how many degrees each one was apart from the other?
90.
Yep, they were all 90 apart. And when you shift them left or right, they're still 90 apart. You just shifted them. So I'm going to use the column I just circled as my labels. So I've got 0. That would be pi over 2, or 90. Pi, or 180. 3 pi over 2, be 270. 2 pi. And 5 pi over 2. Don't label it 1, 2, 3, 4, 5, because your numbers here are awfully messy to work with. Like pi is 3.14, 3 pi over 2, that's 4.7, right? So we don't want to really get into thinking about decimals. And if you do it this way, you don't have to. Okay, so we've got pi over 2, 0. Pi, we're up at 1. 3 pi over 2, back down to 0. 2 pi, you're at -1. Okay, for you guys, I already have graph paper on the test and the homework, so you won't have to sketch. You'll have a place to put it. And then 5 pi over 2, back to 0. Okay, just try to make it look as smooth of a curve as you can. So that graph was shifted to the right. Here's what the original would have looked like. You don't have to sketch the original at the same time. I'm just showing it to you. The one in black is the original. The one in red is the new one. So this graph shifted right, and that's exactly what should happen anytime you subtract. It should shift right. Any questions on that? Okay, so that was a shift by pi over 2 to the right. Let's try a shift by pi to the left. And we're going to use a different function. Okay, now, I'm not going to copy down the original table every single time we do a problem. You've got the original table in your notes. If you need it, look back at it. Okay, step 1, determine what kind of transformation this is. That's a phase shift, because I know I've added or subtracted, in this case I added, in the parentheses. Okay, so for a phase shift, can someone remind me what values stay the same? Yep, the y's. Now can someone else tell me what my y values are for cosine? What are the original values, because they're not changing? Yeah.
1, 0, -1, 0, 1.
Yep. So if that's all you get on this problem, you get 5 points right away for that part of the table. Okay. Now, here's all my x's. I'm going to have 0, pi over 2, pi, 3 pi over 2, 2 pi. Can somebody tell me what am I going to do to all those x's? Right?
Subtract pi.
Perfect. Subtract pi. I don't know a way to help you remember to do the opposite, but you just got to remember, with a phase shift, you do the opposite. Okay, some of these are really quick to do, like pi minus pi is how much? That's 0. What about 0 minus pi? Negative pi. What's 2 pi take away 1 pi? 1 pi. And now the other ones, well, you could do it a couple ways. You could try to figure out what the pattern is, because whatever this value is, it has to be halfway between the one above it and the one below it, because they're all equally spaced. Or, if you don't like thinking about what's halfway between two things, just do out the arithmetic, find the common denominator. So Haley, what's my common denominator here? 2. So I'm going to double the bottom, double the top. And what's 1 pi over 2 take away 2 pi over 2? Yeah, perfect. Negative pi over 2. Which is exactly halfway between negative pi and 0. Without doing the arithmetic, anyone think they can tell me what's halfway between 0 and pi? Because that's going to be the answer. If you want to do it out, you could do it that way.
This is pi over 2.
Pi over 2. Okay. 5 points for the y's, 5 points for the x's. So that table would be worth 10 points on the test. And on a test, I probably wouldn't give you more than like 5 or 6 graphing problems, because they can take a little while. Then the graph itself, this part I usually make worth 2 points. Okay, so 10 points for the table, 2 points for the sketch. Okay, 1 to negative 1. If you want to write your labels above the line or below the line so you don't end up drawing over them, you can do that. I'm going to put my labels down here for that one and that one. You don't need to label 0 because I know the x or the y-axis is 0. Pi over 2 and pi. And if you're looking at that and you're like, well, how is that equally spaced? Negative pi is negative 180, negative 90, 0, 90, 180. Still 90 apart. And now plot your points. 1, 0, negative 1, 0, and 1. Now, this is the one that sometimes people mess up a little bit with the sketch. It's not a V. Okay? What you're sketching is basically that section right there. Okay, so if you ignore everything else, you don't want to sketch it like that. Okay? Keep in mind, it's more of like a U shape. It's the middle part of a wave. Right? So if you were sketching it, it would kind of, here's your wave coming in, and then it would continue on. Okay? You don't have to sketch beyond and after it. I just kind of do that sometime to lead into my sketch so I get an idea of the wave. Okay, so that's generally what our cosine graphs are going to look like because we're sketching kind of the trough of the wave. With sine, we're sketching kind of, I don't know, it's a little different, the part of the wave we're sketching. Okay, any questions on that one? All right, so let's look at the last one. Okay, I'm going to start you off with this one, but then I'm going to pause it and see if you guys can figure out the rest. So Rudy, first, can you tell me what kind of transformation that is? Yeah, phase shift. Yeah, that's good. Phase shift. Can you tell me how do you know it's a phase shift? And where is the subtraction? In, exactly. Anytime it's in the parentheses, adding or subtracting, that's a phase shift. This is totally different. We'll talk about that tomorrow. That's not a phase shift. All right, so phase shift. Faith, what values stay the same when we do a phase shift? The x's or the y's? So which way does phase shift move? Yeah, left or right. Could be either way. So if you're going to move left and right, the x's are going to change. So we're not moving up and down. So that means the y's stay the same. Okay. So I'm going to go back to my original table, fill in my y's. I'm just going to help you with those. By the end of the week, you'll probably have those numbers memorized. Okay. And how about Matt? After I write down my original x's, what am I going to do to all of them?
Add pi over 4.
Exactly. So you're going to take all your x's. And you're going to add pi over 4. Okay, so take a minute or two and see if you can figure out what you get when you add pi over 4 to all of those. A hint is after you do the first two, you should see a pattern in how far apart they are. And then all the other ones have to be exactly the same apart, all the way down. If you don't like looking for a pattern, just go ahead and do the arithmetic out each time. All right, so we're going to add pi over 4 to that one. Did anyone get the next one? Zach?
3 pi over 4.
Yeah, it's going to be 3 pi over 4. Because to get your common denominator, you're going to double the bottom, double the top. 2 pi over 4 plus 1 more is 3. Now, that's a 1. That's a 3. What do you think the next number is going to be in front of the pi over 4?
5.
It's going to be a 5. And then 7. And lastly, 9. If you do out the arithmetic, that's the pattern you get. Okay. Any question on that? Okay, so let's bring this up and start to make our sketch. Okay. Gotta be a little careful when you make the sketch here. That's 1. That's negative 1. There's no problem with that. But let's put pi over 4 right there. What's pi over 4 in degrees? Someone remind me, how many degrees is that? Yeah, that's a 45. Okay. So pi over 4 is 45 degrees. That's 135 degrees. 3 pi over 4. So how far away is 45 from 135? It's 90. It's 90 away. This section right here is worth 45 because that's where we put 45. So whatever you put your first mark at, that's the width of the section. So if the next one is 90 degrees away, would I put it on this mark or would I put it on the second one? I would put it on the second one. If you're going to keep everything equally spaced, that's how you have to do it. If you don't do it that way, you might get a graph that looks something like this. One part of it is kind of squished, the other part is kind of stretched out because you didn't space it equally. Okay? So if you get confused with the radians, pretend like it's in degrees. You wouldn't label something like this. 45, 135. that would be like labeling something 2, 3, and then 4. Well, why is the first gap 2 units, but then the next gap 1 unit, and then 1 unit? Okay, you just have to be consistent. And I know sometimes you can use this symbol. You might have seen that symbol like on your number line. I kind of just stay away from it for this because I think it just confuses more. All right. So I'm going to put these back in radians like they were. All right, so we've got pi over 4. And now we skip 1. We go to 3 pi over 4. And that's going to be the gap each time. So just keep that consistent. 5 pi over 4. Let's see, 7 pi over 4. And on yours, I don't think you're going to run out of room because I made the graph big enough. I didn't make this one big enough. Okay, so 0 pi over 4. 3 pi over 4, you're up at 1. 5 pi over 4, you're 0. Negative 1, this might have been a good one. I should have put the label above it. Then I wouldn't have had to draw through it. Oh. Then back at 0. And everything looks nicely spaced. Well, pretty nicely spaced. Okay, so just remember that. That usually pops up when you have graphs with pi over 4. You just have to be careful with your spacing. Okay, so homework tonight will be a worksheet, maybe 5 questions. I'll put the worksheet in the video in case you need it, but I'm going to give you a copy right now.